So we saw that if we have dynamic data, data in which values are being inserted and deleted, and we want to maintain a sorted property so that we can search efficiently in it, then we need to move from a linear structure to a two-dimensional structure, and we came up with this idea of search trees. So in a search tree, if you remember, at every node you have values, and all the values on the left are to the smaller than v, and all the values on the right are bigger than v. So this tells us how to search for a value. We look at the root node and we can decide whether to go left or right. And remember that in a search tree there are no duplicates. So with this we had this property that if you actually started navigating the tree, you would always walk down a single path, whether you want to find a value or insert a value or delete a value. So therefore all operations on a search tree are actually in the worst case proportional to the height of the tree. But the problem that we saw was that you could have an unbalanced tree. For example, I could have a sequence where I start with an extreme value on the top, and I could have just a linear sequence going down one side of the tree. So this would have height which is proportional to the number of nodes or to the size. So what we would like to do is come up with a way to have balanced trees which have logarithmic height. So if we have logarithmic height, then we are guaranteed that these operations all take only logarithmic time, and so over a sequence of n such operations you will take n log n time, which is similar to what you would do if you do n binary searches on a sorted array. So even though the data is changing from time to time, including the cost of inserting and deleting items and the cost of searching for them using this find operation, everything takes log n time. So over n such operations, if you could balance the tree, you would do n log n work. So our question today is how to balance the tree. So we know that the tree might be balanced to start with, but as we start inserting and deleting items, then the balance will change. So what we need to do is incrementally adjust the balance so that at any point the tree does not become too unbalanced, because it will take a lot of work to reconstruct a balanced tree if it becomes too unbalanced. So we want to incrementally keep the balance. So inductively as we go along, we always have a balanced tree. So to get started on this, we first need to agree on what we mean by balance. Right? So balance roughly means what we think of, right? So if you take a balance in the conventional sense, right, when you go to say the vegetable market, the person has a balance, right? So the balance means that what's on the two sides, the weights that the person puts and the vegetables on the other side balance out, they're about the same. So in terms of a tree, what you're saying is that if I look at a tree and I look at its left subtree and the right subtree, then these two trees must be roughly the same in some quantity, right, some quantitative measure. So we have two quantitative measures that we can define on trees as we have seen. So the first one is size, right? So size is just a total number of nodes. So this is just a total number of nodes, and height is this length of the longest path from the root to a leaf. So supposing we first try to define something on size. Now of course a perfectly balanced tree, now balancing is something which has to happen everywhere. We don't want the tree to be unbalanced anywhere. So at every node we want the same number of children on the left and on the right. Now what happens now is if I have one node, it's fine. If I put something here, I'm forced to put something here because I need them to be the same. Now if I put something here, because this part must be balanced, I must put something there, right? And similarly now because the right must be balanced, I must put something there. So either I have a tree with only one node, or I have this tree with two levels complete, or I have a tree with three levels complete, and so on. So these are called complete binary trees. So you can think, remember in a heap, we might have had a situation where we had only this much, right? So we didn't have these two nodes. So a heap builds up a tree in a kind of complete fashion by doing it level by level, but it's allowed to have some incomplete nodes on the last level. In a complete binary tree, every level is full. So either you have one node, or you have 1 plus 2 nodes, or you have 1 plus 2 plus 4 nodes. So every complete binary tree will have 2 to the power k minus 1 nodes for some power of k, right? 2 to the power 0 minus 1, 2 to the... But now if this is the only situation in which you can meet this, it's obviously not useful, because why? How do we guarantee that over a period of sequences and a sequence of deletes and inserts, that the number of nodes we have has this nice property? So we cannot demand that the size must be equal at every node, because that's too restrictive. It only applies when the size of the tree is a particular value. So we could relax it a little bit by saying, okay, we don't want it to be exactly equal, we just want it to be within 1, for example. We want roughly as many nodes on the left or the right, and this will give us some better way of doing it. But it turns out that maintaining size on the left and the right is very difficult to do in an incremental fashion. So we will not, although this is something which could work, we will do something which is different from this using height. Okay. So remember what height is, right? So height is the number of nodes on the longest path. So you start at the root and you walk down and you pick the longest path among all the leaves that you have. And you see how many nodes you visit. So if your tree is empty, then there is no root, so the height is 0. If the tree has only a root, then the height is 1, because the longest path, the root is also a leaf, the longest path consists of just that one node. In general, if I have a tree, then if I want to find out its height, right, so I will have a height here and I will have a height here, right. So this is going to be 1 plus the maximum of h1 and h2, because the longest path from here is either the path that follows the longest path on the right, or it is the path that follows the longest path on the left, and in either case I am taking that longest path in my left or right subtree and adding this one node to it. So it's 1 plus the maximum of the heights of the left and right subtree. So this is how you formally define the height. So what do we mean by a height balanced tree? Right? So let's assume that there is this function in our Python notation called height, which we can apply to a node and it will return the value of the height. So what we really want is the height of the left subtree, self.left.height, and the height of the right subtree, self.right.height, should not be more than 1 off. So they need not be equal, but they cannot be more than 1 different from each other. So they must be within 1. It doesn't matter whether self is left is more or right is more. Okay? Either of them could be more, but the difference should not be more than 1. So it turns out that we can actually maintain height balanced trees, and height balanced trees are also called AVL trees, and this is named after the 2 people who first discovered it. So there is a Russian mathematician, computer scientist called Edelson-Velsky, and there is another one from the West called Landis. Right? So both of them in some sense parallelly discovered this class of trees and how to manipulate them to maintain this height balance. So these height balanced trees are also called AVL trees. There are other types of balanced trees which you can use, but we will not look at them. We will only look at this particular one to illustrate that it's possible. So of course now we have chosen something plausible. We said, okay, we have size and height, and we kind of, without giving a proof, we said that maintaining size balance is difficult. So we decided to opt for height balance. But the whole purpose of this was to get this logarithmic height. So how do we guarantee that if we have a height balanced tree and we have n nodes, the height is proportional to log n, right? So we first have to establish this mathematical fact, otherwise there is no point in going for a height balanced tree, because it doesn't serve our purpose of making everything logarithmic. So what we want to try and see is how bad can it be, right? So bad in this sense means that I would like height to be small with respect to size, which is the same as saying that I would like size to be big with respect to height, right? I want the size to grow as a function of height very fast. So what is the smallest size I can restrict a tree to if I give you a given height, right? So this is our, so what is the minimum height balanced tree of a given height? So if it is 0, we know it's the empty tree. If it is 1, then we just have this trivial tree consisting of a root node, because that's the only tree of height 1. If it is true, it's easy to see it's either this one or it is the one symmetrically which has a right child, right? I want height 2, so I have to have a child of the root, but I want to have the smallest number of nodes with such a property, so I don't put the other child. I could also put both children, but then I would get a larger tree, right? So the goal is to find the minimum size tree that is height balanced for a given height. So by inspection, it's easy to see that for 2, I can either put a left child or a right child, and I will get a tree with just 2 nodes which has height 2. What about 3 nodes? Well, for 3 nodes, first of all, I need to construct a path of length 3. That's the minimum that I need. Now, once I construct a path of length 3 on one side, then remember that the 2 sides cannot differ by more than 1. So I am forced to construct a path of length 2 on the other side. So I am forced to put something on the other side. but that can be only one node because I don't need to put more than necessary, and because of the property that this part is already height balanced, I don't need to put a right child at the bottom, and I don't need to put, of course, anything there. So for height of 3, I can get away with a tree which has only 4 nodes, right? So basically, if I have 0 height, I get 0 nodes. If I have 1 height, I get 1 node. If I have 2 height, I get 2 nodes. If I have 3 height, I get 4 nodes. So it doesn't seem as though we are getting very far in terms of bigging. Our goal is to say that if I fix h, then size must be large, right? And it doesn't seem to be growing very fast. It's growing very slowly, as a matter of fact. So how would we actually proceed to the next level? If I want to find, now for 3 we did it by kind of inspection, but by 4 it's not very clear. So if I draw a tree of height 4, right, I first have to construct a path of length 4. And then I have to start balancing it all over the place. I need to make sure that this part is balanced, so I need to put something here. Then I need to make that this part is balanced, so I need to put something there, and so on, right? So how do you systematically construct the next level tree, which is small with respect to the height height increasing by 1 more, right? So it turns out that this, in fact, is, I mean, up to symmetry and all that, of course, all these things, remember, are symmetric. I could have drawn this tree also by putting the thing on the right hand side, for example, right? So there are many possible ways of drawing these trees. So up to symmetry, I claim that this is the smallest tree you can draw of height 4, which is height balanced. Now if you look at it closely, you will see that on its left it has this tree, okay, and on its right it has this tree. And this is not really a coincidence, because if I want to increase the height by 1, then the left subtree must have height -1. So if I want the overall height to be 4, I need something on one side which has height 3. And I want the smallest possible tree of size of height 3. So I already know how to do that. I take the smallest possible tree of height 3, I know its height balance, and I put it on the left hand side. Now in order to keep this height balance, because I put 3 there, I must put something which is 2 on the other side at least, because otherwise the difference will be more than 1. So I take the smallest possible tree of height 2 and put it there, right? So this is the general strategy, right? If I want to build a tree of height h, which has the smallest number of nodes possible, I will first find the smallest tree of height h-1 and stick it on the left subtree, because that h-1 plus the new root gives me a height of h. Similarly, I will take h-2 and stick it on the right hand side. Again, I want the smallest tree of that size, right? So if I keep incrementally finding the smallest tree of every size, then when I get to h, I know the smallest trees of the smaller sizes, so I can stick the correct ones together to get myself a height balanced tree, which is smallest possible of size h. Right? So this is our, I mean, we argue that this is the smallest tree that we can construct, which is height balanced and has a given height. So our goal is to show that these trees are growing fast. So notice that up to here it looked like it was growing slowly, because I had, remember, 1 node here, 2 nodes here, 4 nodes here, but here suddenly I have got 1, 2, 3, 4, 5, 7 nodes here. So there is some hope that things are actually growing faster than that the next level would be even faster, because remember, the next level will have this on the left and this on the right. So it will have 7 nodes on the left and it will have 4 nodes on the right. So overall this will have 7 plus 4 plus 1, it will have 12 nodes, right? So there is some apparent increase in the growth. So can we quantify this? So let us try to define this function. So the capital S of h is the size of the smallest tree we can draw, which is height balanced and has h, right? This is what we want to calculate. How big is, or how small is S of h compared to h? So we have seen that if the height is 0, then it is 0, right? The size of the smallest tree with height 0 is 0, and for 1 it is 1, that we drew. Now our strategy tells us that the way we construct the smallest tree of size of height h is to first take the smallest tree of the lesser height h-1, take another tree of h-2 put on the other side, so that this node is balanced, and then I have to account for the new root that I have put in, so I have to add a 1, right? So that is what we said here. If I go here, this is 2 plus 1 plus 1, so I get 4. Here I get 4 plus 2 plus 1, so I get 7. right? And the next one, as we said, will be 7 plus 4 plus 1 will give me 12, right? So this gives me this recurrence which says that S of h is 1 plus S of h minus 1 plus S of h minus 2. So how do we figure out how fast this grows, right? Why is this going to become a large number? Well, I am not going to show you why it grows fast, I am just going to show you why it should grow fast compared to something which you may have seen or you can go and look up very easily, which is the Fibonacci sequence. So if you remember the Fibonacci numbers, you start with 0 and 1 and then you keep adding the previous two, right? So the next number is 1 plus 0 is 1, the next number is 1 plus 1 is 2, then 3, then 5, then 8, then 11 and so on, and these numbers grow pretty fast. So the recurrence for this is that the 0th Fibonacci number is 0, the 1th Fibonacci number is 1 and the nth Fibonacci number is the sum of the previous two, right? So if you look at this, the big difference between our recurrence and the Fibonacci recurrence is that we are adding 1. So we are not just taking the previous two values, but we are adding 1 to it, right? So what this says is that S of n is definitely bigger than or equal to f of n, right? Initially it is the same, but after I get to 2, it's going to become bigger because the second Fibonacci number, if you notice, is 0 plus 1, whereas here I get 2, right? So the size of this tree is growing at least as fast as the Fibonacci numbers with respect to the height. And now you have to go and find out for yourself that the Fibonacci numbers grow exponentially. So the nth Fibonacci number is actually exponential with respect to n. So given that the nth Fibonacci number is exponential with respect to n, the size of the h height tree must also be exponential with respect to h, right? So this rests on the argument that Fibonacci gives you an exponential growth and the size of this smallest tree of height h is sitting above the Fibonacci sequence because I am actually adding 1 with respect to what I would be computing if it was a Fibonacci sequence. So with this argument, we are now showing that the size grows fast, and if the size is exponential in h, if I turn it around, then it means that h is logarithmic in the size, right? So if n is the size, then n will be exponential in h, so h will be logarithmic in n, that's what we want, right? So this justifies mathematically why height balance trees are of interest to us. If we can maintain height balance, then we can actually get logarithmic height trees, and if we can get logarithmic height trees, as we saw, all our operations on search trees will be proportional to log n. So the difficulty is that this balance gets disturbed when we change the tree. So how much does it get disturbed and what is some measure of imbalance? So from a natural perspective, supposing somebody holds up a balance, as we said, with weights, right, and it is not balanced, then it will tilt to one side. So let us try to quantify this slope. So let us say that the slope at a node is the difference in the height between the left and the right, right? The slope could be now positive or negative because it's not the absolute value. It's saying take the left height, subtract the right height. If the left height is more, you'll get a positive value. If the right height is more, you'll get a negative value. So our definition of height balance says that these two quantities cannot differ by more than 1. That means the slope can be 0 if they are both equal, or it can be plus 1 or minus 1 depending on which one is more. So there are only 3 legal values allowed for the slope of a node in any balanced tree. Now what happens when we insert or delete a value with respect to a balanced tree? So if we insert a value, so remember that I could have a tree which looks like this, and supposing this has slope plus 1, right? So the left hand side is already more than the right hand side by 1, and remember what insert does, right? It walks down until it finds a leaf where it can't locate the thing, and then it sticks a new value there. So it will now increase the height perhaps of the longest path on the left by 1, and so the slope will go from plus 1 to plus 2. And the same thing could happen on the right hand side, right? Instead of this, if it had been minus 1, it could have been that I come here and add something and it becomes minus 2. So insert can clearly make something go from plus 1 to plus 2 or minus 1 to minus 2, and delete can do the same thing in reverse. So supposing this is already plus 1 and then I delete a node here and this tree actually shrinks, then the tree which had a plus 1 balance becomes plus 2 because the shorter side has shrunk. right. So in general, if we try to arrest this imbalance as soon as it happens, then I claim that the only slopes that are of interest to us, which are outside the balanced range, are plus 2, minus 2. It cannot be worse than that, because I have only deleted or inserted one node at this point, so the height has not changed. So notice that that's all that happens if you go back and look at the search tree things, right? It either increases the length of a path by 1, or it decreases by deleting the maximum. It deletes one path by 1. So how do we fix this balance? So the general way to fix this balance is by moving things from one side to the other, right? There are too many things on the left, you move it to the right. There are too many things on the right, you move it to the left. But you have to do it in a sensible way to respect the search tree property. Remember, the search tree property says that the root must be in between the values on the left and the values on the right. So let's first look at the case where there's too much on my right, right? So the right has a height of h plus 2. So this is where we have a slope of minus 2 technically, because the left minus the right. Right, the slope is minus 2, so I have too many nodes on the, I have too long a path on the right subtree. So I want to bring things from here to here. So in order to do that, what I will do is I will first expand this tree. So notice that this has height of at least 2, because h plus 2, h can be at least, cannot be smaller than 0. So there are at least two things. So there's at least one node and then one more node. Okay, there's at least two nodes on that path there. So I can pick out the root of this and then split it into two parts. So if I expand this, what I mean by expand is I focus on the root of this, the right child of the original node, right, which I will denote with this diamond symbol. So the diamond symbol is a different value from this dot symbol. Right? I don't know what they are, but I know that the diamond is a bigger value than dot. Right? So what do we know? We know that everything here is smaller than the dot. Everything here is smaller than the diamond, bigger than the dot. Everything in R is bigger than the diamond, right? So I have three different groups of values. So everything in the leftmost tree is smaller than everything. Everything in the L tree is between the dot and the diamond in value, and everything in the R tree is bigger than both the dot and the diamond. Now I want to transfer something from here to there, but I want to do it in a kind of local way. I don't want to go down and move things around. So I want to do some surgery at the top of the tree. So the surgery at the top of the tree will mean that I'm actually going to take this and kind of make it like this, right? So let me just draw it properly. So this is my rotation, right? So I've taken this and I've promoted this to the root. Instead of being the right child, it now becomes the root. So what was the root now becomes the left child, right? So that is my rotation. But now I have to make sure that all these other values are in the correct place, and I want to do a minimum amount of work. So remember that this was to the left of everything, so it remains to the left of the black dot. This was bigger than everything, so it remains to the right of the diamond. And this was bigger than the black dot and smaller than the diamond, so now it is smaller than the diamond, bigger than the black dot. Right? So by just keeping track of the original property of what these values had with respect to the nodes above, you can figure out where to do this, and as we will see that this rotation actually is very easy to implement, because I just have to change some left-right pointers at the top of the tree. I don't have to go deep into the tree too. So I only need to do a constant number of changes. So this is a left rotation. I take things from the right and I kind of rotate the tree, but in the process some big chunk from the right actually comes to the left. Right? It's not just at the top, but some stuff from the right also comes to the left. And of course, what happens here, if you now look at the slopes carefully, okay, let's try to analyze what has happened, right? So first of all, we said that there was a difference of 2. So let's assume that the left was h, then the right must be 2 more, okay, exactly 2 more, because that's the only case we're interested in, so h plus 2. If this is h plus 2, then something below this must be h plus 1, right? So this says that either the left tree is h plus 1 or the right tree is h plus 1 or both, and because it is balanced, there must be at least h. Right? So it says either I could have h plus 1, h plus 1, both are h plus 1, therefore the diamond is at h plus 2, or I could have h and h plus 1, so that the diamond is still at h plus 2, but it is balanced, so there is a difference of 1, or it could be the other way. Right? It cannot both be h, but just for conciseness I have written it like this, but this plus this is not possible. Okay? I cannot have a situation where I have this and this, so that is not allowed. So now when I move these things, of course I am not destroying any nodes, so the nodes are still the same. So this tree is unchanged, so this remains of height h, and these trees are also unchanged. So what is the worst that could happen? The worst that could happen is that this actually was h and this was h plus 1. Remember, either possibility was there. So if this is the case, then this is at h plus 2, right? And so this thing has actually gone to something which has a bad slope, right? So this is, from here it's coming as h, so the difference between the right and the left is actually plus 2, right? So it has gone from minus 2 to plus 2. On the other hand, the good case is that this was h and this was h plus 1, right? If this is the case, then both of these are h, so this is at height h plus 1, but this is also at height h plus 1, so I actually have a 0. So I could have a 0, and if now both are h plus 1, then I will have h plus 2 here and h plus 1. So I could have any of these, and remember, I have gone from minus 2 to plus 2. So on its own, a rotation need not fix the imbalance. We will see that you can combine rotations to fix the imbalance, right? So this is a left rotation. I take things from my right subtree and move it to the left because the right has too much. I could do the same thing the other way, right? So there is symmetric right rotation which takes things from the left and moves it to the right. So now my left is too tall and I want to move things to the right. So again, I expand the left exactly as I had done before for the right. So this is a completely symmetric operation. Now I am going to take things from here to there, and again I observe that this is extreme left, this is extreme right, and this is in the middle, right? So after I move it by the same argument, what will happen is that this remains to the left of everything, right? And this remains to the right of everything, and this will come now between these two nodes. So it comes to the right of the diamond and to the left of the black dot. And by the same argument, I started with a plus 2 slope, and in the extreme case I might end up with a minus 2 slope, because this could be h and this could be h plus 1, so this could be at height h plus 2. Or I could get a 0 slope, or I could get minus 1 slope, right? So we have these two rotations. They are symmetric operations. They are exactly the same except they go in opposite directions. So let's see how to implement it. So this is now the left rotation, the first one that we saw. So we want to take this and go there. So we are going to rotate at this point. So this is my self. Okay, I am applying the rotation at this node marked V. So what I am going to do is I am going to create a new node here, right? And I am going to copy V there, and I am going to promote. So I am going to basically do some surgery on this tree. So I am going to create a new left child, and what am I going to put there? I am going to put this value V, right? So how did I get the value? I first said what was the value that I started with. So that value, this is a little bit like inserting at the beginning of a linked list. I am going to copy the value that I have one position down. Okay, and then I have to now take these three trees and put them in the right place. So I have a left tree, this is TL. I have a right left tree, that is if I go right and left, and I have a right tree, right? So I have these three trees, and of course I have a value there also which I have to preserve. So finally what I end up doing is I cannot change my current node. This is the basic principle. I cannot change the node that self is pointing to. So I have to copy whatever VR has into self, right? So I am going to have self dot value has to be the value of VR, and I have to set its left and right correctly. Its right is going to be whatever it already was, which is the right tree that the node was pointing to. The left is going to be what it already was, okay, which is this one. This is the new node, right? And the new node now has on its right this tree TRL, which was so I am just doing, now notice that this is a top level constant number of operations. I am doing some 5 assignment statements, then I am creating a node, and I am doing some 4 more assignment statements, right? So it does not matter how big the tree was underneath. I am only doing some surgery at this top level. Right? I am only interested in exploring the top level of this tree and making some local choices. So this is a constant overhead. Making a rotation at the root of a tree takes a constant amount of time independent of how big the tree actually is. And of course now you can obviously imagine that the right rotation is symmetric, right? So I copy the current value as V. Now I take the value from my left and keep it as VL, and then I create a new node to the right. Okay, so this is this new node, and then I populate it with my current root value, and then I put the right trees, I hang off the trees correctly, right. So I take this tree and I hang it off the root, I take this tree and I hang it to the left of this, and I take this tree and I hang it to the right of this, right. So this is the rotation. So rotation is very easy to implement given our existing Python description of the tree as a class. So that doesn't take any effort at all. So what we have seen is that you can take a tree with balance +2 or -2, and we can do some rotation and transfer the balance to the other side. It may or may not fix it. So now we need to make sure that we fix it. So we now want to use this to actually, so rotation so far is not itself a balancing operation, it is a basic block for balancing. So let's see how to rebalance. Okay. So remember that the only two situations that we will ever rebalance are when the node is +2 or -2, because we are rebalancing at every point. We are never allowing the balance to become worse than +2 or -2. So it was previously +1 to -1 in that range, and we did one insert or delete and something must have changed, so it might have become +2, might have become -2. So let's look at the +2 case, right. So in the +2 case, the left hand side is bigger than the right hand side. Okay. So since it is +2, okay, we must have something here overall. If this is h, this left hand side must be h +2. So as before, we have expanded this h +2 with this diamond as the root node, and now I am going to look at the slope at this point, right. The slope at this point is +2, that I know. What is the slope at the diamond? So the slope at the diamond now, can it be something other than -1, 0, 1? Well, we are going to argue that it cannot happen, because we are always going to ensure that, I mean, we will see that this rebalancing happens in such a way that when I am touching a node and trying to rebalance it, we can assume that its subtrees have been recursively rebalanced, because remember that all our updates happen recursively. So what we will see is that every time we make an update, we rebalance. So at every point below, we have already rebalanced before coming here. Okay, so that's what we have to keep track of. So we can assume that this tree capital L and this tree capital R are already balanced. Okay. So now we have to look at the slope, as I said, of this diamond node. So what are the possibilities? It's going to be either 0 or +1 or -1. So I'm going to consider first the case where it is not -1. It's either 0 or +1, right? If it is 0 or +1, remember that this whole thing has to have h +2. So one of these two things has to have h +1. And it cannot be only the right hand side, because then the slope will become -1. So the left hand side must be h +1, it cannot be h. The right hand side could be h or h +1. If it is h, I have 1. If it is h +1, I have 0. Okay, so this is a concrete picture that we have under the assumption that the root node, that black dot, has a slope +2, and the left child, the diamond node, has either 0 or 1 as its slope. Okay, so now I want to rectify this using those rotations that we have just seen. So it turns out that here a single rotation is enough, right? And what does that single rotation do? Well, I just rotate at the top. So I will basically, if I erase all this, right, I am applying essentially a right rotation at this node. And that's exactly the right rotation that we saw earlier. We'll take the diamond node and we'll hang this node off it, and then this right tree will remain there. This R tree will come here, and this L tree will be here, because that's the relative values of L, R, and that original tree on the right are like this, right. So this is what we get, right. So we get this tree here. Okay. So now what we can see now is that the height here is positively h +1. Okay. The height here could be h +1 if I only look for this, but it could also be h +2, because this is h +1 +1, but in the worst case it's h +2, it cannot be more than h +2, right. So the slope of this node now, okay, this node which came from the left, this value that came from the left, okay, it is either 0 or it is -1, because it is 1 less on the left than on the right, but it is within range, right. So all the nodes you can see are balanced, because everything below this is definitely balanced, and this node is balanced because it is either +1 or 0, right. Either the right, this tree named R is either h +1 minus h is +1, or it is h minus h is 0. So if I have the, going back, if I have the diamond node having a slope of 0 or 1, a single rotation at the top fixes the problem for me. Unfortunately, if it is a -1, it's a little bit more tricky. right. So, supposing the slope here is minus 1, then I know for sure that this must be the situation. This has to be h plus 1 and this has to be h, because I need to get a height of h plus 2 at this point. The only way I can get a height of h plus 2 at that point is to have one h plus 1 child, either left or right, and I know which one it is because the slope is minus 1. So, since this is h plus 1, I will expand this tree. I am going to expand this tree now, right. So, I am going to redraw this tree and say that, okay, under this thing there is a star, that is the third node which I have kind of pulled out. So, I am explicitly extracting the root of that tree, and it has these two subtrees which I am going to call x and y. So, this together, this whole thing before was what I had called R, right, the capital R. So, this whole thing together was earlier this capital R. Okay. So, I have taken this capital R and decomposed it into the root and there is two subtrees. So, this whole thing before was h plus 1. Okay. So, this should be h or h minus 1, right. So, at least one of them has to be h, but the other one could be h minus 1, but not both, right, because if this whole thing is h plus 1, then one of these two trees must be of height h. So, now I take this thing, right, and I expand it and I have rotated it at this point, right. So, I take this, and I rotate it here. So, originally my balance, the problem is here, but I am not going to the root at all, I am doing it at a lower level. So, I am first rotating the left subtree of the root. Okay. So, I rotate it this way. So, again remember that this must be h minus 1, it does not matter, as we will see, it will work out okay. So, now we have this situation, right. So, in this situation I still am not promised something, because I could have an h plus 1, okay, and so I could have an unbalanced situation because of h, so this could be at h plus 1 and this could be at h plus 2, and I know that this is at h. So, the situation here could still be bad in the sense that it could still be a situation where I have plus 2 at this point. I have not changed the imbalance at that point by doing this rotation inside, but now I will do that previous rotation. Actually, now it turns out that I am in this case with respect to the star node. So, if I do one more right rotation, right, then you can see that either everything is h or I have h and h minus 1. So, basically these two nodes are balanced because they have either 0 or plus 1 minus 1 slope, and these two nodes are at the same height. So, this node is balanced, right. So, in case I have one situation, a single rotation suffices, another situation 2 rotations suffice. So, the rotation on its own, as I said, does not fix the balance, but by combining the rotations cleverly, you can always fix this thing in a constant number of operations. Remember, each rotation took a few reassignments of the nodes near the top of the trees. So, this was for the plus 2 case, and we saw that everything is symmetric. So, here we did a right rotation and a left rotation, there you do a left rotation, right rotation. Okay. So, it is the same thing, but you just do it symmetrically. So, if you can do plus 2, you can do minus 2 by just applying the rotations in the opposite directions. So, how does this all fit together? Well, we saw the code for rotate, right, and what we described now was a procedure of how to apply this rotate by looking at the slope. So, if you combine it, I have not shown the code, if you combine it, you can combine these rotations judiciously, so that when you have slope plus 2, you can make it back to a normal slope, and when you have slope minus 2, you can make by doing the rebalancing appropriately. So, we can assume that we can take those rotations and stick them together in the correct sequence to always take a node and rebalance it whenever the slope is outside the permitted range. So, our goal therefore is to keep it always within the permitted range. So, what we have to do is go back and check the code that we have that modifies the tree. So, what is the code that modifies the tree? Insert and delete. So, wherever we modify the tree, that subtree must be rebalanced. So, if you remember insert, it said, okay, if it is empty, then I create the value here, which is not a problem because that is a balanced tree because it has only one node, right. And of course, if I find the value, I am not making any change. If I go to the left and I insert it, then potentially I have to rebalance it, right. So, after I insert on the left hand side, the left hand side might change and therefore I will rebalance it. Now, notice that this node, okay, so I am going here and I am saying rebalance this thing, but the insert could have come to me from above. So it will now at the next level ask to rebalance this node. So that's what I meant by saying that this rebalancing happens bottom up. So when I change something to my left, I ask my left to change itself, to rebalance itself. Now when I return the value back up, the parent who delegated this insert to me is going to ask me to rebalance myself. So I will get rebalanced after my child is rebalanced, and therefore this rebalancing up assumption that the rebalancing is working bottom up is validated. And the same thing holds, of course, when you do the right hand side. If you insert on the right, you do a right rebalance. And similarly, when you do a delete, right, there is the empty case which we don't have to worry about. But if you delete on the left, you do should be left, right? If you do delete on the left, you rebalance on the left. If you delete on the right, you rebalance on the right. Okay. Now notice here, when you delete the maximum on your left subtree, that will in turn create its own rebalancing. So you don't have to separately rebalance it. It's only when you kind of do it yourself that you have to do it. Okay. So all this requires one extra step which we have kind of not looked at very carefully, which is we need to determine the slope, right, in two senses. First of all, we need to check when we rebalance whether we are in the range of +2, -2, otherwise nothing is to be done. And even when it is +2 or -2, remember we have to look at the child and decide whether its slope is +0, +1 or -1. So we have to repeatedly find the slope of a node, and the slope of a node, we said, is determined by computing the heights of the two children and taking the difference. So this is the Python code which expresses what we said at the beginning, that the height of an empty tree is 0 and the height of non-empty tree is 1 plus the height, maximum height of its children. Notice that this also takes care of the leaf, because the leaf will be 1 plus the two children which are empty trees. So it will be 1 plus the maximum of 0 and 0. So the height of a leaf will turn out to be 1, as we would expect. So the problem with this particular thing is that in order to compute height, we have to go down the whole tree, because I have to look at the left subtree and the right subtree, and in turn when I look at the root of the left subtree, it will look at its left subtree and right subtree. So in fact, every height computation will traverse all the nodes. It's not like find or insert, which says either go left or go right. Right? All our search tree operations so far were clever in the sense that they never went down both paths. Either it said go down the left path or it said go down the right path, but never both. But this is now requiring me to go both ways, so it's going to be actually an order n operation. And this is going to kill me, because even though the final product is something which is balanced, if I am doing order n work each time in order to find the slope and rebalance it, then my rebalancing is already a linear operation. So I am going to do n into n squared operations at the minimum across my entire work. So we cannot afford to do this, so we must do something more clever. So the solution is to say that I don't need to compute the height, because I can incrementally update the height whenever I change things around. So what I do is I actually keep, in addition to value, self.value, self.left, self.right, right, I keep an extra field called self.height. And self.height basically can be updated by taking the maximum of the left and the right. Okay, so do not. This is not definition of height. The definition of height is just to return self.height. But whenever I do an update, this is what I need to do. So if you look at the update, for instance, right, so whenever I rebalance and the heights have possibly changed, I will update my height, and incrementally and inductively I assume that my children have adjusted their heights. So their height field is correct. So I can just look up the height that my left child reports and the height that my right child reports, and add 1 to the maximum of these. I don't have to recursively go down, because inductively every node has maintained its height in this local variable. Right? So by keeping a local variable height, I am able to keep track of the height as we go along without recomputing it wastefully going up and down the tree. So this is the extra trick that you need in order to make the rebalancing work, is to keep the height explicitly recorded as part of the node along with the value, the left child and the right child. So there is an extra local integer that you have to keep. Right, so what we have seen is that these binary search trees, which we introduced as a two-dimensional data structure to keep track of sorted values which are changing with inserts and deletes, can be kept balanced by doing these local rotations. So by combining these rotations judiciously and by keeping track of the slope, we can actually keep a height balanced tree, and we proved that height balanced trees are good enough. Right? A height balanced tree is weaker than a size balanced tree, but it still has the property that the size overall is exponential in the height, or the height is logarithmic in the size. So this guarantees that whenever I do find, search, or insert or delete, which walks down a single path in the tree, that cost is never more than logarithmic in the number of values that I am maintaining. So overall I get this over a sequence of n such operations, no matter which of these operations it is, it's not going to cross n log n. So that's the beauty of balanced search trees. These are not the only, so height balanced trees, I should again remind you, are not the only way to keep balanced search trees. There are many other types of ways of keeping balanced search trees, which you can read about if you look at algorithms books, but this is one of the simplest ones to explain, and you can see very readily why it maintains the balance and why this balance gives you this logarithmic height.